So here is how Deutsch's algorithm proceeds, and I will show you in writing. So Deutsch's algorithm proceeds as follows. It starts with 2 qubits in the state ket0. Then the first step is to prepare the state ket plus, ket minus. So to do this, we first apply an X gate, so a flip on the second qubit, an identity on the first qubit. So this results in the state ket0, ket1. And then we apply a Hadamard gate on both qubits. And this results in the state plus, minus. This is just by definition of the Hadamard gate. Now the second step is to apply the gate UF. And so this results in the following state. UF, ket plus, ket minus, which we can rewrite as UF. And then the first qubit is 1 over square root of 2 ket0 plus 1 over square root of 2 ket1. And the second qubit is in the state minus. Now we can rewrite this as UF applied to 1 over square root of 2 ket0 ket minus plus 1 over square root of 2 ket1 ket minus. And now by linearity of the action of UF, this is the same as 1 over square root of 2 UF ket0 ket minus plus 1 over square root of 2 UF ket1 ket minus. Now we have to remember what we showed earlier in the previous module. In particular, in the second approach, when we put the second qubit in superposition, what we showed was that UF applied to ket x ket minus is equal to minus 1 to the f of x ket x ket minus. And now we plug in this expression at this point, and what we get is that this is equal to minus 1 to the f of 0 over square root of 2 ket0 ket minus, right? This comes from this term here, plus minus 1 to the f of 1 over square root of 2 ket1 ket minus. And now I'm copying over this last expression so that we have a little bit more space. So we can rewrite this by grouping the terms of the first qubit, because the second qubit is always in the state ket minus. And so this is equal to minus 1 to the f of 0 over square root of 2 ket0 plus minus 1 to the f of 1 over square root of 2 ket1. This is for the first qubit, and the second qubit is just in the state ket minus. And now the expression for the first qubit should look somewhat familiar to you, because we have encountered it already in the exercise at the beginning of this video. And so if you have forgotten, feel free to pause the video and go back to the beginning and look at the exercise again. So what we showed there was that this expression is equal up to a global phase, in fact up to a factor of minus 1 to the f of 0 is equal to 1 over square root of 2 ket0 plus minus 1 to the f of 0 XOR f of 1 over square root of 2 ket1. And then again we are copying the state of the second qubit, which is ket minus. And so this is up to a global phase. And now notice that we have finally obtained what we wanted. This is because if f of 0 XOR f of 1 is equal to 0, then the first qubit is in the state plus. And on the other hand, if f of 0 XOR f of 1 is equal to 1, then the first qubit is in the state minus. And so at this point, the second qubit has served its purpose. We can just ignore it. And now we can tell whether the first qubit is a plus or a minus, as we mentioned earlier, by applying a Hadamard gate. And so the final step of Deutsch's algorithm is to apply a Hadamard gate on the first qubit and then measure. And if the measurement outcome is 0, then we know that we had a plus state and we were in the first case. And so the function f is constant. And if the measurement outcome is 1, then the state was a minus and the function f was balanced. So this is all of Deutsch's algorithm. Now, I strongly recommend that you go over all of the steps of Deutsch's algorithm and make sure that every step is clear to you. So I'll conclude with a recap of Deutsch's algorithm, which, after all is said and done, is actually pretty simple. So the algorithm starts by preparing the state ket plus on the first qubit and ket minus on the second qubit. It then applies the 2-qubit gate UF, so it queries the function f. Then it applies a Hadamard gate on the first qubit. And finally, it just measures the first qubit. And if the answer is 0, then the function f was constant. If the answer is 1, the function was balanced.